back in April or May, whenever I gave you this first part. Eyepiece, we went through talking about the different aspects, the different parts of them, the way in which different terminology like eye relief and such is to be defined, and if we talk about it, you won't find it too confusing. Talked about elements and groups, what goes to make up eyepieces. We did the important stuff, like trying to figure out the magnification of your telescope, where you realize that what you've got is two optical trains, a telescope from here to here with a pointed end this way, and an eyepiece with the pointed end this way. So you put the two pointed ends together, and it's the ratio of this focal length to this focal length that gives you your magnification. Okay? Just a few other things. We talked about exit pupils, apertures, how they vary with your eyeballs, what works for your eyeballs, what happens when you try to push the envelope and end up with weird things in the middle of your view. Odd things that can happen with eyepieces, especially a lot of the new wide-angle ones that you should not be too concerned about. That's just the nature of the beast. Some of the problems with eyepieces, the different ways in which eyepieces can fail you, and the way in which we're always talking about the kind of failures that eyepieces have. Even issues where the eyepiece isn't the problem. Then we got into talking about things like different mechanical problems with eyepieces, where you get reflections and odd kinds of things in eyepieces. We talked about the way in which some eyepieces will only be sharp at certain places in the field of view. We talked about the dreaded coma that you can get from telescopes and how this can make it look like eyepiece problems. Some of the different distortions that eyepieces can suffer, we went through all of that, and that's where we left off last time. Good. So you got all that. There will be a test on that later. So today we're going to hopefully slow things down a bit and talk about the other aspects of eyepieces that might have a few of you people wondering what to do. First thing we're going to discuss is eyepiece formats. We've got the three major ones up here now. The one on the right here is the 0.965 inch eyepiece size that's otherwise known as the Japanese standards. The Japanese use this as a standard size eyepiece for quite a few years. The 1 1/4 inch eyepiece that we're all familiar with here is otherwise known as the American standard, and it's the most common eyepiece size that you'll see. 1 1/4 inch. When you see the small eyepiece size, everyone thinks, uh-oh, crappy department store telescopes. And that's very true, but there are some incredibly good eyepieces out there made by Takahashi and JSO and such. So just because an eyepiece is in this little format doesn't mean it's necessarily a bad eyepiece. And then the larger 2-inch eyepiece size, which used to be known as an observatory size eyepiece, but now everybody's getting into it because we've got telescopes now, especially once we had the Dobsonian revolution, and we got into these huge wide fields of view. We needed eyepieces that were able to help give us those wide fields, and we'll talk a bit about that later. The first thing to realize about eyepieces is telescope companies have learned that this is one way to keep your wallet flat. And this is a picture showing not even all the eyepieces that TeleVue makes these days. I mean, the other brands can have lots of different choices as well. But this just shows you how many different eyepieces are out there, even from just one brand. And not all of them are included here. They've got even more than this. So there's tons and tons of eyepieces to choose from, even from one particular maker. And the thing to recognize in all of this is you don't need half of them. You don't need a quarter of them. You don't need a tenth of them. we'll talk about how many you might want to have or need.
Jerry,
Yeah.
that's not what Mike said.
Never mind, yeah. Mike is different. Mike's got special needs. Here's some of the more common types of eyepieces that you might get with a telescope, especially a lot of these Kellners, which can be also labeled as MAs, modified achromats. And those will be a lot of the very simple type eyepieces that you might end up with. Some come with flossels as well now. There was a time in the 1970s when flossels were cutting-edge eyepieces. They cost a fortune, and only a few select people had them back then. Now they're the new norm, the modern eyepiece. And stuff like the fancy ones from Teleview are the new exotic eyepieces that everyone is lusting after. And we'll mention more about this oddity right here, the Barlow, in a bit. Here is a graph showing the different ways in which eyepiece designs can be laid out. You can range all the way from the very simple ones, like a Ramsden eyepiece. Up here, you don't see too many of them except in some real old cheapy stuff. You will come across some exotic use of things. Here's your flossel, for instance, and that's not the only way with your flossel. Here's another design, this variation on the flossel, the Brandon eyepiece. The orthoscopic, this is the eyepiece that was always considered the gold standard. It was an eyepiece that, while it didn't have a very big field of view, it was a very faithful representation of what was up there in the sky. You could use orthoscopic eyepieces to measure the distances between stars and know you were getting it right. Other eyepieces, especially our new wide field ones, they introduce linear distortions in the field of view, and you can no longer trust them to have stars at the right distances from each other. Sometimes you'll see this in the form of the barrel distortion and the pincushion distortion that we talked about last time. But otherwise, if you do need to have a nice accurate view of something in the sky, that, for instance, there used to be a wonderful time when people studied double stars and measured their positions and such. This seems to have fallen out of favor these days, but it was an orthoscopic eyepiece that you want more than any other to do this. It was the most faithful of all the eyepieces, and in some ways still is, if it's positioned in your field of view that is of concern to you. You can run through so many more of these here. I'll just point out ones like the original daguerreotype that really gave us the wide field revolution. The king of them these days is the Bowler, which gives you a 120-degree eyepiece field and going even past the Teleview Eco. And a few other bizarre designs too, with many complicated pieces of glass in them. The colors actually denote types of glass that goes into these things. So you can see just how complicated and diverse eyepieces can be in all kinds of ways. For the most part, you don't have to worry about that. You want to go argue this stuff on Cloudy Night's website, fine. But if you If you're using a big undriven Dobsonian telescope and it's not tracking objects, it'd be nice if you didn't have to move it every couple of seconds. A wider field of view allows you to watch the object longer before having to nudge it along. That was one of the motivating factors for that. Now, the interesting question is, and I think I've got this diagram up here. Here's a sort of general diagram of everything from the tiny Kellners. The reverse Kellners would be close to an orthoscopic Plossl. So this is the Plossl eyepiece field. 60-degree Erfels, which are the sort of the old version of wide field eyepieces, is this one. 68-degree field is getting out to here. The 82-degree field of a Nagler is out to here. 100-degree field of the Ethos, and then the 120-degree field of the Kohlers, showing just in relationship how much more sky you're looking at. So notice, even though it goes from 50 to 100, that's more than twice the amount of sky you're looking at, because this is area, not just diameter, that you're grabbing. So you're seeing a lot more stars when you go to the wider field of view. It's also more, on an aesthetic level, it's more immersive. You feel like you're looking at things much closer when the eyepiece, the edge stop, the field of the view that you run up against the edge, when it isn't small and looks like it's at the end of a tube. Now, at the other end of things, you do get these 82, 100, and 120-degree Kohler eyepieces. And what you're going to hear, especially given the marketing stuff out there, is bigger is better. And they charge you more for it, so it must be a better eyepiece. No, no, no. It's not necessarily the case. And matter of fact, I find, from a personal point of view, from about the 82-degree field of a Nagler is just about it. Anything more than that, and I find it distracting because I have to start looking. I like to be able to see the edge of the field of view. I like to know everything I'm looking at. And then you've got this eyepiece where you can't see the edge of the field just by scrunching your eye up against it. You can't see the whole thing. And then you have to start bobbing and weaving around to catch things out on the edges. It's annoying, it's distracting. I don't need these eyepieces. I might have some for sale. I don't know. I'm supposed to commercialize these things. Okay. Now, the interesting thing is, all of this stuff, comparing the size of these eyepieces, is just there to help us figure out what the field of view that the eyepiece is going to give us. It's what we look at when we hold an eyepiece up and just look at the round circle in there. That tells us nothing about the true field of view, or how much sky we're actually looking at. So the big lesson in all of this is, remember, I put an A in front of field of view here, because this is the apparent field of view. There's also should be like a T here, for true field of view, which is the amount of sky you're actually looking at. And now we're going to turn to the relationship between the two of those things here. So, the true field of sky is some tiny little, acreage up in the sky that you're looking at. Some tiny little circle, usually a half a degree, maybe 1 degree, maybe 2 or 3 degrees at most. As opposed to the apparent field of view that starts out at least 40 degrees and can go to as much as 120. Now, the interesting thing here is the relationship between what your eyepiece does, what your eyepiece and telescope do to this acreage to turn it into this acreage is your magnification. I like the British term when they talk about magnification, because they say, well, how many diameters is that? And what they're talking about is, how many diameters more is this than that? Is that 50 diameters more? Or 50 power, the way we talk? Their language is a little bit more literal, a little more graphic, getting you at the idea of the relationship between the true field of view out there and your apparent field of view. This true field of view is going to vary on the telescope that you put it in. The apparent field of view is a property of the eyepiece. The eyepiece will be 65-degree apparent field of view, and it'll always look like 65 degrees unless you do something horrible like stop down the field and get some weird vignetting going on. Now, there's a few formulas here and everything, but I think the easiest way to remember how to grab what you're looking at is through something like this. Remember, it's a relationship between the size of the true field of view and magnification and apparent field of view. So, if you know the apparent field of view of your eyepiece, and you should, it's usually in the information on it. And then you know the magnification because you know the focal length of your eyepiece and you know the focal length of your telescope. And you divide the focal length of the eyepiece into the focal length of the telescope, you'll get its magnification. So you'll have these two values, and you'll be able to get a good approximation of the true field of view, how much sky you're looking at. Now that's really important to know when you start to go star hopping. You want to know, I'm supposed to go 5 degrees over. Well, how far is 5 degrees over in my telescope? Well, if you do the calculations and find out that the true field of view that you're looking at in the sky is, say, 1 degree, you know you're going to have to go 5 fields of view over to do that 5-degree hop. That's the kind of thing that is useful to know with your setup so that you can be a far more effective star hopper. There's several ways to calculate this true field of view, and I've listed some of them here. For instance, I listed this one because this is the real operative in what's going on here to limit the field of view. You'll see all kinds of discussions and arguments about how field of view is determined, but the absolute limit is really the field stop diameter. And if you remember that first picture I showed up there with 2 little lenses and a little piece of metal ring going around the outside, that's the field stop. You'll see it when you turn your eyepiece over. There should be a little ring on the inside. When you look through your eyepiece in the regular way, you'll see the edge of your field of view. You're looking at the field stop. On some eyepieces, they've stretched that format to the maximum amount it'll use, and there won't be a separate ring. It'll be the barrel of the eyepiece itself.
Quick question here.
Sure.
57.3, what does that represent?
This diameter is in terms of radians. It's a calculation that uses radians in the geometry. So to turn it into degrees, you multiply, because there's 57.29365 degrees to a radian. So,
Thanks.
yeah, it's just a matter of geometry and such. Now, all of this stuff will give you this, but if you're unsure about it, and these are just rough estimates of what's going on, there is an absolute way to tell what you're looking at as far as acreage in the sky. It's called the drift method. And all you do is you time how long it takes for a star to drift across your field of view. And of course you want it across the maximal part here of your field of view, so no, I'm skipping across one of the edges this way. And you can make this very simple by doing something quite easy to do. Find a star near the celestial equator. And you don't have to do a cosine correction. Because I know once the word cosine comes in, we're turned off and we don't want to do this anymore. So, find, like, this Alnitak is a star in the belt of the Orion. And that star is pretty much right on the celestial equator. So it's a real easy star to find. It's bright enough. Find the star. Put it at the edge of your field of view, right on the edge there. And turn your drive off if your telescope has a drive. And just time it to see how long it takes to cross right over. And then you do a really simple bit of arithmetic. It's not even algebra, it's just plain arithmetic. And you'll be able to figure out your true field of view. And here's the explanation for why this is the thing that it is. So you'll be able to always get an absolutely correct value for your true field of view if you have the sky to look at. Now, the relationship between this true field of view and the apparent field of view, and why we have the formats and eyepieces that we do. Here is two views of what looks like the Pleiades, a really bad picture of it. One through an orthoscopic, which has a very small apparent field of view, and the big, wide-angle colossal that supplanted it as the most favored eyepiece. And you can see that even though they're the same magnification in a particular telescope, and you know that because both of them are 25 millimeter, the apparent field of view of the colossal being larger allows it to see more of the sky. So, the advantage of these larger formats is that it allows us to get larger apparent fields of view in our eyepieces. But each format has a limit. And the limit in each format is when you don't have a field stop anymore. You've got an eyepiece that's, because remember, you're looking for your widest field of view, which means your lowest power view, which means you want eyepieces with longer and longer focal lengths. One of the great crimes in astronomy, for instance, let's just talk the 1 1/4, since that's the most common and the one I know the numbers for. But in 1 1/4 eyepieces, you could get wider and wider fields of view as you go with longer and longer focal lengths. So you'll see more sky in a 20 millimeter than a 15. You'll see more in a 30 millimeter than in a 20 millimeter. You'll see more. It's lower power. It's taking in more of the sky. It's not magnifying it to see some smaller part. Okay? Now, the problem with the 1 1/4 inch, once you get to about 32 degrees, 35, not degrees, millimeters, and so you're getting lower and lower power. Once you get to eyepieces with focal lengths of 35 millimeters, the optical path is now filling the 1 1/4 inch tube. There's no room for a field stop. The tube itself is essentially the field stop. And the crime I was mentioning is, in the 1 1/4 inch eyepiece format, you'll see 40 millimeter eyepieces. And you'll think, okay, I should get a 40 millimeter eyepiece so I can see an even wider field of view. The problem is, a 40 millimeter focal length in a 1 1/4 inch format is actually stopped down a bit. It's not allowing the full light cone to be used. And when you look through a 40 millimeter eyepiece that is in the 1 1/4 inch format, it's small. It'll be even smaller than this. You can just hold the two up to your eyes and you realize, I've been robbed. And what's happened here is that you're not getting any extra value out of your eyepiece by going to a 40 millimeter eyepiece in the 1 1/4 inch format. If you want to see the whole sky that's allowed at that low a power, you got to go to the 2 inch format. So you can start to see what's happening here. Everybody thinks, well, you want the wide fields of view. We like the new eyepieces with the enlarged apparent fields of view, even much larger than our colossals. So we want to buy all these eyepieces with, ultra wide fields of view. They're engaging. They're wonderful. But remember two things. One is, they're there to give you that wide field of view only if you're using them at really low powers. And there is some trade-off here. There is some advantages to some things. A 68-degree field, apparent field of view on a 24 millimeter eyepiece will give you the same amount of sky acreage to look at as your 32 millimeter colossal would, and with a 50-degree apparent field of view. So there's lots of trade-offs that start happening in certain ranges, but at the extremes, each of these comes up against the optical limits of things. There are other kinds of eyepieces that help with different problems with telescopes. I've just mentioned two of them here. This is an old one designed by Heinz. If you've ever looked through a really fast, like by fast I mean an F ratio of like 4 or even 5 in a Newtonian telescope. The edges of the field of view will have little ice cream cones all pointing outwards, essentially. Stars won't be good, clean focus. That's due to coma. Now, he designed an eyepiece here to help to correct that. It works great in the designed telescopes, like the telescopes it's designed for, which are these fast Newtonians. You put it in your refractor, and its correcting ability actually makes the view worse, because the refractor didn't have that problem to begin with. It has other issues. So eyepieces can be tailored and customized to help get rid of certain problems. Some eyepieces, like we talked about, would have a curvature to the image plane. It wouldn't be flat like the ideal, but it would have some curvature to it where it comes to the focus. Now, if that curve is opposite the curvature that your telescope added to the view, hey, you might be better off. So just because an eyepiece worked better in this one telescope, don't think that it's going to work better in all telescopes. Which brings us to a really good question. Why don't telescope companies manufacture eyepieces that would be dedicated to correcting the problems of their scopes, and we'd all be much happier? This over here is the modern version of what this was. This was a dedicated eyepiece that was to get rid of coma. They decided, no, that's not a really good way to go about it. Teleview and good old Uncle Al Nagler came out with his paracores here, which were adjustable and can correct varying amounts of coma depending on how fast your Newtonian reflectors are. So that's the modern version of dealing with some of these problems. Here's a few claims to just round up about what these eyepieces are all about. A lot of people have this issue saying the cheaper the eyepiece, the more problems it has. But you can buy a lot of cheap Blossels and orthoscopics that are essentially perfect eyepieces for what they are. They aren't the widest of fields, but they're quite fine and adequate the way they sit. Then you're going to hear this up, and this is an actual quote, saying the next step up in quality and price are the super wides. One step above are the ultra wides. So the marketing people are saying wider is better. Well, you'll have to decide that for yourself. I found my range, and anything much more than about 70, well maybe to 80 degree field is plenty good enough. I don't like anything much more than that. And if it works in this fast scope, it'll be best in slower scopes. One of the things you pay for is the ability of an eyepiece to not only work in your slow F10 Schmidt-Cassegrains, but it'll also work in your very steep light-coned Newtonians. And if it's an expensive eyepiece to correct in both cases, great. It might not actually be the best thing in your F10, and you're probably wasting money if all you own is an F10. To buy these exotically correcting eyepieces that are really made to correct much steeper light cones. And this statement too, the only eyepiece you'll need at that magnification. I've got about 3 different kinds of eyepieces in the normal range, the 20 to 24 millimeter range. And I use all of them. And like I said, if you've got a different telescope, you may find it far more suitable in another scope. And sometimes you just need a particular combination of things to make it go. And having a second eyepiece when it's minus 30 outside is always a good idea because you can frost it out. So, some things up here. What do you need in the way of eyepieces? You can probably get away with about 3 eyepieces and a Barlow. But just don't get a 10, 20, and 40 millimeter eyepieces. Because then your Barlow, when you Barlow your 20, it'll act like your 10. Well, that didn't help you. You should get maybe a 15 or a 25, so that when you put the Barlow in there, you're not duplicating a focal length you already have. So you don't get just simple multiples in your eyepiece range of whatever your Barlow is good for. And realize that even though there's some 2-inch eyepieces that are 10 millimeter, I think I have a 10 millimeter coning that's in a 2-inch format, totally useless. That could have been quite easily done in a 1 1/4, and would probably work fine in the Japanese standard as well. So when you come to low-powered eyepieces, realize what you're trying to do is maximize the field of view, and if you're going to be able to use the 2-inch format, that's where you can go beyond that magic number of 32 or 35 in certain cases. A medium, normal eyepiece, usually one that comes with your telescope, it's usually not a bad eyepiece, it'll work there. And then you need something in the high power range, and make sure you just don't duplicate it with a Barlow. So those 3 eyepieces and a Barlow gives you a choice of 6 different magnifications. That's quite an adequate group. And if they're really good quality eyepieces, you may find you don't need anything more than that. And if you really can't find what you're looking for in the wide, vast field of eyepieces out there that are available now, people are making their own. And you might decide to do that too. That's the end of that.
How are we doing here? Good feedback. Sounds like it must be working. I don't know what I can click on here.
This is the beginners.
Well, welcome to the delayed November meeting. Doesn't seem to be as big a crowd as it was last.
It came here last Friday.
I guess we don't have enough giveaways. You'll notice we have 6 books. This is a package of stuff left over from the Space Society meeting earlier this week, including this lovely -3 only best. And there's free magazines over here. And Kevin's giving away this AstroTech.
Generous, but I'm not that generous.
My name is Jay Anderson, for those of you who haven't met me, and president for another 3 meetings. Welcome. How many of you are here for the first time?
Oh, I know this gate.
You're just getting old and forgot that you were there. Maybe you'll forget what you want for this telescope. Well, we've had the beginner session. I'm going to do the announcements. Brian is going to do What's Up. I know he's here. Ian is doing What's New. I haven't seen him yet. He was pretty much under the weather this morning. So we'll see whether he can come in. Russ is Russ going to tell us something about a Mars stove he owns here. He has a Venus stove here. And we're going to get a dark sky update about our association with the Nature Conservancy, and also from Dennis. Coffee, cookies, and conversations. We are being a little more rigorous about not having food in this room, so the goodies will be moved just outside. I think we could probably leave the coffee here, or take it outside. In other words, we'll consume it outside of the room here. We do have to bring them back in when we're done, because the leftovers get consumed by passing students. We cleaned ourselves out of cookies after we came back into the meeting. And then we have Andrea to speak to us on balloon science. I picked the title, but a very interesting subject, and something that probably many of you are familiar with and yet not familiar with. And pizza tonight will be at Boston Pizza. Now, one of the first things I want to do, Council had a meeting and we decided that it was time to award the 2015 awards. And we usually give them out after the year is over. We're just a little slower at doing it this time. So the first award I wanted to mention tonight is for this scene. Most of you will know this as the Spruce Wood Star Party. And we have decided to award the service. Many years into organizing the Spruce Wood Star Party, and frankly I'm delighted that you've been doing it because it's been a tremendous success. So we have the engraved plaque that will go up in the observatory, and we have this one for you that you can show your children and prove to them that you actually do go someplace on Friday night.
Well, I am honored to accept this. Thank you so much. And everybody says this, but I'm so happy to be part of this club because the people in this club are amazing. And this is why I do this Star Party, because it's where we get together and we have fun for 3 whole nights at Spruce Wood. So thank you so much. I'm really honored.
For those of you who think to make like to be president after me, this is one of the perks. So we have 2 awards that we give out. And the next award goes to somebody who seemed to generate, he seemed to find clear skies when nobody else did. He was out when nobody else was out. I don't know if he's here tonight. He did tell me that he too was under the weather, but we decided to award the Achievement Award to Kevin Delta. Is Kevin here tonight? And he said he had the flu and that he was going to see if he was up to coming tonight, but frankly, somebody with the flu is probably best to stay away from us. How many of you had your flu shots? So anyway, we have also engraved the Achievement Award plaque to go up inside the observatory. And Brian, I'll give these to you. You can take them up there next time you're going. And I also have a plaque for Kevin as well. So when we see Kevin next door, send him an email and congratulate him. He said he was rather delighted to receive the award. As you know, the RASC owns the magazine Sky News now, and I've brought in some spare copies of Sky News. If you're unfamiliar with it, but all of us get it as a part of our subscription. So if you're not a member of the RASC, help yourself to it, and you'll see it comes with your membership. They have sent me a note from National saying that I promote the use of Sky News. I think probably because we earn advertising revenue. But they do have quite a nice little site with keeping up with what's happening in the week. So you can supplement what Brian's going to tell us for the next month with what's happening, especially new stuff that comes along. One of the things about Sky News, you go in there and you take a look at their photo of the week. And I see a lot of the photographs that come out of this club. And let me tell you, there's a lot of you who could have the photo of the week quite easily if you just send in your contribution to Sky News. So I think that would be something that we should think about doing if you've got something really neat. It doesn't have to be deep sky image. It can be aurora the night before, or planetary conjunction, or even stuff in the sky that's not typically related to astronomy, such as weird cloud formations or halos, especially, and sundogs and rainbows and stuff like that. Sky News is pretty good about covering a wide range of things. So you can put Sky News on your taskbar there, or your favorites list, and check in it occasionally. Another thing National wanted us to think about was planning for the 2017 total eclipse. So I know many of you are planning on going to it. It's not that far. We've covered this over many times before, but there's the path of the eclipse. You can see that Winnipeg is just outside the 80% coverage in the high 70s. When you go with the actual percent of the sun that's covered over, as opposed to how far across the sun the moon is, it turns out we're a little over 70%. And so this will be a pretty dramatic event for people in Winnipeg who stay behind. And we've handled the partial eclipse several years ago with a whole bunch of glasses and things like that. And our plan is to do that again. We have the resources. We will perhaps be a little more careful about buying our solar filters from National, because the ones they picked for sale last time were pretty awful in quality. And I've let my feelings be known about that. And they don't seem to have realized that those glasses were really awful. Maybe they need to hand it to some of the people in Toronto who go to solar eclipses and ask them to evaluate them. I don't know why, they just didn't give you a very clear image. National is probably going to work on a brochure. We can make our own as well, maybe a little less Toronto-centric or Ontario-centric. But one of the things we'll have to do is to decide what we're going to do. We're going to go to Assiniboine Park again and handle several thousand people. Do we go to a couple of different parks? And the other thing is how many of you are going to still be here to actually do it. So we probably form a small committee in the first few months of next year to handle what we're going to do, because this is an American total eclipse. It's going to have enormous media presence, far, far more than the partial eclipse that we saw 2 years ago. The General Assembly in Ottawa is coming up on the July 1st long weekend, and the reservations at Assiniboine College, which is being held in Ottawa, to get assured space, you have to make the reservations by next month. And so we have, among the people we elect for our council next year are 2 representatives to go to Toronto or go to the General Assembly at least subsidized rates, if not completely paid for. And that's something you might like to consider, to have Ian to see our national capital at 150th anniversary of Canada. So if you've got it all thinking about doing it, now is the time to make a decision on reserving some space in the residences at Assiniboine College.
I'm pretty sure that's Algonquin College.
Is it? Did I? You might be right.
Assiniboine up there.
Yeah, Assiniboine doesn't sound like the right place, does it? Oh, well, one of those colleges. What's it say in the website? Oh yeah, well, General Assembly, Ottawa, there it is. The reminder that the university's open house is held at the end of the month, last Wednesday of the month, which is the 30th, the last day of the month. And you'll note it's sponsored partly by this center, the RASC, which means that one of us has to be there to sort of hand out a few brochures, show people the handbook and a copy of Sky News, basically show them what you get for being a member of the center. Unfortunately, I won't be able to make that, but Stan's been standing in pretty well for us in the last couple of meetings. He's not here tonight. Some excuse about his daughter getting married tomorrow. National awards. They're not as important as the awards we give out, but there is a list of some of the national awards, most of the national awards. Those awards are for fairly specific fairly specific achievements. The Champ Medal goes to the person who proves Einstein wrong, and that's generally accepted by the physics community. You have to really do something significant for astronomy, usually in the nature of science. Ken Chilton Prize is for amateur astronomers who contribute to serious astronomical research. And it's gone in the past to people who have done variable stars and asteroids and discoveries of supernova and things like that. President's Award goes to anybody the president wants to give it to for whatever reason the president decides. It's sort of one that he gets to work. The ELAC Award goes to communications, public outreach. Simon Newcomb Award is for writing, books, pamphlets, I don't know, maybe the websites. And service awards are the ones that we see most involved in, and you can get service awards locally, as Sylvia did tonight, but you can also get national service awards, and you just have to be nominated. So the most important thing for us is if you think somebody should get a service award from this community, then let's nominate them. And you should go through the list on the RASC website and find out who hasn't already had service awards from national in this center. Because certainly a number of people have. Randy Atwood, who is our executive director, would like to have those nominations. But if you want to, you think somebody should be nominated for some of these awards, let me know, and we'll see if we can work on putting together in a way of a nomination form. He's also floated the idea at the end of July of having a national star party. In Toronto, it's probably darker in July the 29th than it is in Manitoba, but it's a rather convenient time because of where the moon is in relation to Saturn and Jupiter. He's just looking for a kind of, what do you think? Just to reiterate, for those of you who are contemplating a telescope, that we do loan them out for a month at a time. And we have one here today to go out, plus this donation from Kevin. Winnocentrics. I have had two people express an interest in becoming the Winnocentrics editor. Nobody's actually said to me, well, send me the stuff yet, but we will be running with a new editor for the next issue, and we've been Megan has been pretty successful. Megan, I put your name still down here, but I don't think, that's because I don't have a new name to put in. But anyway, been pretty successful about picking stuff off of our discussion list and putting it in. Plus, it's not a very hard job to do, but if you feel like it needs some artistic changes, then you certainly can have the freedom to do that, providing that center council is not too unhappy with it. And just to make sure that you're in line with all of the discussions, get the memos, there's the process for getting into the email list if you're not already there. If there are any difficulties with it, Ian Cameron is still looking after the email list, even though he's retired from the university. And he has a new email, so if you can't contact him because your mail program keeps popping up his old address, then just ask me and I'll give you the new one. And so, this brings us back to our schedule. To Brian with What's Up? Are you loaded already, Brian?
Right here.
Not in the sense of beer focus.
Jay, our second award winner for tonight has made an appearance. He is here. Our second achievement award winner.
I can't hear you.
Kevin's here.
Kevin's here.
Where is he? You put your hand up. Right over here. Come on down. You should at least get to see this. Although if you're out at Glenlee in one of your normal visits, then you'll be able to get it on the. Anyway, thank you very much. That was, you made it, put me to shame for sure with all of the material that was coming out from you. It was a, yeah, right, thanks. There was a new galaxy every couple of days from you. All right, well, that was quite an impressive amount of photography.
All right, so this is what we have up for November. We're already halfway through the month, but I'll do my best to explain it. All right, for the planets, not much really happening for the planets. Most of them are pretty low in the sky, maybe except for Mars. We'll have a look at it, but they're pretty much not going to be very observable, if you ask me. I'll tell you why. So this is the off the bottom view of the solar system that we have here. You can tell. Well, there's Earth, right? And then we have Mars, Neptune, Venus, Mercury, and Saturn. They're going to be pretty much low in the sky to observe. And if you look from Earth, and this is what, roughly about 6 p.m., you can tell that we have Saturn, we have Venus, Mars, and Uranus there. So that's pretty low in the sky, and it's pretty early in the evening to really do any kind of observing. Except for maybe a little later on. This is, what is it? Okay, sorry, that's for today. I said, well, 4 o'clock, we have Jupiter's going to start rising around 4 o'clock in the morning. Now, I do mention something about the comets, but none of them are really observable. They pretty much have the magnitude of about 12 or 15, so not much there. Sorry, too far. We do have some asteroids. There's a comet here. This series is somewhere around here. I can't really see it. But 4 o'clock in the morning, there's another comet here. I'll have a chart here to better explain what's going on with the comets. But now, during the daytime, you did notice that we do have 5 planets that you can see pretty much. Well, we have Jupiter here. We have Mercury, Saturn, Venus, and Mars. But that's what, 5, 6 planets there during the day. You can observe some of the planets during the day if you really look closely. Apparently you can look at Saturn, I believe, and Mars during the day if you know where to look. And yeah, some planets are observable during the day, but just be careful of the sun. Okay, so what do I have here? For the last couple of weeks, some of the members have been out there with me. One of the things that they're really pretty much amazed is some of the deep sky objects I like to show with the LS200, if it doesn't run away, which is M13, M92, M57, the Ring Nebula, M27 Dumbbell Galaxy Nebula, and of course M31, the Andromeda Galaxy. And the reason why I like to pick those objects when it comes to new members, if the LS200 doesn't work out very well, it's easy for me to find them. Of course, I do have a couple asteroids here, Pallas there, but curious. Okay. Now, what do I have here? Around 10:30, if we do have a members' night tomorrow, The moon's going to start to rise around 10:30, so the sky doesn't look too bad. And of course, a lot of people are asking about M42 Orion Nebula. It's, you can see it here. So after 10:30, it's pretty much high in the sky to do some observing. We do have another comets here, but again, some of those magnitudes are just way too high to do any kind of observing. What else? Oh, it's that Catalina right there, that comet there, at the beginning of the year. Now its magnitude is apparently, 15. So, anyways, next, this is something I shot last weekend. Yeah, it was like the full moon, right? I think around, 12 o'clock in the morning. And it was in the city. And of course, there was a lot of post-production after to do it. It was Image plus Photoshop, and then back to Image plus to actually get this image. It was only about 24 seconds exposure and about 10 subs, and that was about it. So you still can do some imaging during the day or at night with the full moon. What else? Okay, for the calendar of celestial objects for that month, well, we're pretty much halfway through the month anyways. We have a torrid meteor shower north and south on November the 12th. Now on November the 14th, everyone commented about the supermoon, right? It's pretty close, about 356,000 kilometers. But of course, the next 4 days, you have those tidal waves. We have the Lyrian meteor shower that peaked just, this morning actually. But of course, I think it was pretty cloudy, but of course I had to work. And of course, the moon is the 30th of November 27th. Now, what do I have here? Okay, well, the north and south here at the moon shower, okay, it's pretty much over, but, and what is it? I think this is supposed to be south and the north. There's the constellation Taurus. Okay, so I think I did try to do some observing for that, but again, I didn't really see much about it. Now, the Lyrian meteor shower, haven't mentioned that on the meteor, right? I don't have it here. Okay, so it's not really a good example here. Do something with that. I remember Leo here. Just to see a little bit of the meteor shower here. So right about here. Anyways. The projected value was supposed to be about 20 meters per hour, but because of the full moon, you might get one or two, but of course, I don't think anyone really watched it. All right, so like I mentioned about the comets in November, like I said, much of the magnitudes are pretty too high for to do any kind of observing. Okay, and then I have the phases of the moon, just kind of give you an idea. Maybe starting next week and start doing some more imaging on it. And that's it. That's all I have for what's up.
Russ. Yep. Well, I come up here, Marshall. I guess you want some points up here. Yep.
So my name is Russ, and I'm just going to do a little showing
from there, there's really not much to see as far as detail. This is a full relief Mars bowl. And it's about 28 inches in diameter, just shy of that. The reason why it's 28 inches in diameter is when I started this project, I had to think about it's something you can't turn or fold or whatever through a world. So I had to make sure when I started this project, I didn't get too carried away. Something that would be locked in my basement and I'd have to take out a wall. I started this project back in the late 80s. There was an astronomy magazine article, and it was about making a little relief diorama of the volcano region of Mars, the Tharsis Bulge, where most of the large shield volcanoes are. And so anyway, thinking about that a while, I thought, well, instead of just making this little thing out of plaster of Paris, why don't I just try and see if I can make a whole Mars globe? And so starting off, I couldn't find a suitable ball. You think, so you can't just go to the store and get a sphere. Now you can, of course, with the internet, you can do searches. This is like in the late 1980s, or early 1990s. So how I first began is I went to the Manitoba Museum's library, and I was looking upstairs once there, and I was looking at all these atlases, and here's a Mars atlas. And I thought, well, this is pretty cool. I started looking through it, and it's like, it's got all of Mars done up in grid pattern, all these what they call quadrangles, and it provided me all the latitude and longitude, and it's like, okay, well, this is easy to plot onto a sphere. So of course, again, this is pre-internet. I don't know how I found it. I took down the information, and I guess I found through a library sort of like a contact phone number or something, and found out that there's such a thing as NASA Publications. I don't know if it's still around or if it's changed into a different name. Anyway, I bought it for $30 at the time. I thought, well, that's a good deal. So this is the 1 to 5 million series, Atlas of Mars. So I'm guessing that every inch in this book is going to be 5 million inches long or high or whatever on the real planet. Now, of course, again, I couldn't find a sphere that was suitable. There are these large balls that sit on hydro lines, and they're so that aircraft can identify the lines. And I actually got one of those. My local hydro office, they had a cracked one. So I looked at it and I thought, okay, I'm just, no questions asked, I'll take it home and worry about the details later. Turns out it's a little more capsule, actually, than it is nice spherical. So what I ended up doing is started carving a sphere out of styrofoam and using a template, sort of like a semicircle template out of plexiglass. I just kept moving it around, anchoring it at the poles, and moving this plexiglass template, semicircle, around the globe, and just working the material down until I got a fairly close styrofoam ball. Then I thought, okay, well, now I need to make it stiff or hard so that I can put the detail on it, and I started to put on plaster cloth, plaster of Paris, the same stuff they use for casting broken bones. And it seemed like a good idea, but it was becoming so heavy that it was like counterproductive. It became so heavy that it could actually flex under its own weight. So I kind of abandoned that idea, and rather than throwing it all away, I decided, well, okay, we're going to go even more extreme and start fiberglassing it. So I got the resin, got the cloth, and fiberglassed it, and made a ball. And out of that ball, I had to, again, coat it with resin mixed with very fine sawdust. And this will give me tooth to eventually put on what is this hard crust, I'll call it. And so the crust is actually about 3/8 inch. It varies a little bit over it, but it's about 3/8 inch thick, and it's a mix of polyfilla. It used to come in little buckets, and polyfilla is extremely hard. If you ever, don't ever buy polyfilla for filling your wall holes and cracks and stuff, because when you put it on, I mean, it all seems nice until it comes to sanding. It's extremely hard, and you'll end up sanding the whole wall around the patch. So it's very hard, but it's also very brittle. So I did a lot of playing around, finally came up with my little secret recipe, which was adding Wellbond glue. And Wellbond is something that can be added for concrete repair. It's like a PVA glue or white glue on steroids. It's very tough, and it made it extremely tough too. I mean, this thing has been dropped a few times. Granted, on carpet from this height doesn't do anything to it. Now the craters. So yeah, I ended up plotting all my latitude and longitude, and all the craters on it are, you know, people think it's kind of simple to do a crater. All you have to do is build up detail and build up walls. Well, when you look carefully at photos of the moon or Mars, you'll actually see the crater floor is actually slightly recessed from the surface. And so to duplicate that, I ended up having to actually gouge down most of all these craters on here. I think there's like 2,000 of them. It's been too long since I remember that number, but it seemed to me to be a couple of thousand. And so in order to recess them, it's like, what can I use? Because I tried, I used a rotary tool, like a Dremel, and I would put bits on there, and it turns out these bits, they gum up too fast, and that's partially because of the Wellbond glue. It gets hot under the friction, because these tools, you know, even at their lowest setting, they still produce a fair amount of heat and friction. So it heated up, gummed up, and it's like, hey, this isn't working. So I ended up making my own bits. So I would take a nail, just a regular, you know, wood nail, and I would take little plugs. You know, when they plug screw holes or nail holes in furniture, you can buy them at a hobby store mostly, or that kind of place. And I would make my own little sort of cut pieces of dowel or cut these little plugs, and I'd epoxy them onto this and use this as my bit. And you get the nail size that fits in the chuck of your Dremel. And then what I would do is I would just cut little squares of whichever written sandpaper I wanted to, and I'd use silicone. And just put a little dab of silicone, put the piece of sandpaper on, and let it cure overnight. And the next day I could just go around with a nail clipper and trim off all the edge, so I had a nice little round. And then I would just, you know, mark out. I would do this Mars globe like one quadrangle at a time, because otherwise you get just far too, you lose track of where you're going. And so it would just recess the crater a little bit. So that's the first part of the process. The second part of the process is now you have crater walls, because it looks kind of odd if you just have recesses. You have to have these tiny little buildups, the rim of the crater. And so what I used for that is called Liquitex, has a product called modeling paste. And so a little bit of trial and error. What I would do is I would actually take and I did this for most of the larger craters, you take a toothpick, and it'd have to be just the right wetness of modeling paste, and you just dab the edge of the crater that you just recessed, and you dab it all the way around, you let it dry just a little bit. And then I would have several popsicle sticks, because they have rounded edges, it's their ends. And I would make some the standard size, and some of them would be, you know, a quarter of the width of a popsicle stick. And then I would just kind of push outward, and I would build up just this tiny little bit of a ridge all around. It gave a better look to it. And then, of course, there are little mountainous regions or hilly regions, gray areas, and rougher areas. And there you would just take a paintbrush and you would just dab the modeling paste and just keep playing with it until you built it up to give you the right kind of texture, the right kind of look. And Valles Marineris, which is the big valley on Mars, that was done mostly with several different widths of chisel. And once that was done, I had my prototype finished. And there were quite a few years in between the start of the project and when I actually finished it. And the Manitoba Museum expressed an interest. I guess it was one of the really good, I guess the last big opposition of Mars, probably about 10, 12 years ago. Can't remember quite. And the Manitoba Museum, the planetarium, expressed an interest in purchasing one of these and having it on display for this couple of months in the fall of that year. And so what I did is I ended up doing molding and casting. And that's another whole area that gets just so technical and so frustrating. A sphere is one of the hardest things on this planet to reproduce using resin, because you think, okay, I'll make it in two halves, and then I'll do my molding and casting, and I'll put my two halves together. They never turn out the same. If you have a little more material on one side, it'll shrink more than the other side, and so you're playing with this equator that doesn't want to line up properly. And so what I ended up, or finally found, was a product called marine epoxy, and it has one of the lowest shrinkage factors compared to regular fiberglass epoxy. And so I used that. I made a large rubber mold in two halves, and then I would paint in this, it's called a gel coat, and I would paint in the resin, and that would pick up the detail from the rubber mold, which was from this. So it's quite a process. It's very time consuming. But in the end, I did come up with several partial casts, which I kept for myself. And I did manage to get two nice halves that I mated and epoxied together for the Manitoba Museum. And went to an auto body shop, got what I call paint bombs, which is just spray cans of primer, and prime the whole thing with gray primer. And of course, that's when you reveal all of the stakes and all the seams that aren't seamless. And so you rework it, and you reprime it again, everything looks good, and then what you do is, again, you get spray bombs from the auto body shop, and they can just match exactly what you want. The reason why I use spray bombs is instead of acrylic base, I use a solvent base, because it's far more, it's much tougher. I mean, you can scratch it and wipe it, and you know, nothing shows up. And flaking is not as big an issue either. So I did that for the Manitoba Museum, and again, I made partial molds for myself, because every time you do casting, you pull the molds off, and you're just losing a little bit of material here and there, and it starts to take details away. And so it was after about 3 or 4 attempts at doing a whole one, I just decided I'm going to do a few partials and retire the molds, so it's somewhere in a landfill. And so I'm just left with this now. And I did paint, of course, for the Manitoba Museum. I did paint it up and did all the all the surface colorings, surface markings. And I found a guy's website. This is now during the time of internet. I found a guy's website who used to do the airbrushing for the Apollo missions. He would do airbrushing of the first maps where they could plan moon landings and just have better, take the raw radar images and make nice water airbrush prints out of them. And he was retired at the time. He lived on a boat in a marina, and on the internet he processed and made these images that properly detailed radar images are real. They're kind of a mishmash and they're really hard to interpret. And so he really cleaned them up, and so I downloaded a bunch of information from him and put all these dark areas, light areas, all that to give it the proper detail. And so now I've had this in my basement a long time. It's just not really suitable for my home. I've played with it for a long time. It's sort of like, how long do you want to relive that college football game? And it's like, you know, I've had fun with it, I'm done with it, and I'm moving on. And I do want to sell it if anybody wants to see me later, see me after the meeting. It cannot be used, it can possibly use to be, to make some more molds, but at this point, I think you'd be pushing it. And also, in order to paint this would be pretty tough now, because in order to make a mold, you need to put on what's called mold release. And mold release, it can be oily or it can be waxy, and it's extremely hard to remove. And even if you can remove it, you end up starting to kind of rub out or smooth out. It softens up your detail.
Wow.
I'll just say at the break, when people are welcome to come by, take a look. I'll flip it in a way so that you can see most of the more interesting features. And all I ask is don't spill coffee on it. Thanks.
Wasn't expecting that one, because I got a little model of ours I'd like to bring in. A 30-year model.
Dennis. As you know, we've been going back and forth with the Nature Conservancy for a couple of years now on how we can use their dark sky site to the south, and Dennis has been instrumental in following up on that.
Can you hear me okay? Yeah. So anyway, just actually a pretty quick update. The area we're looking at is, technically it's their Weston Family Tallgrass Prairie Turbidge Center. We've been out there a few times. Really want to say thank you first to Jerry and Sylvia, because they started a lot of this work with Jay early on, a few years ago. But just so that people understand what we have to do to get a dark sky preserve, that's what we're working with the Nature Conservancy to do. The process is, there's a lot of different things that have to go on. So the first major process that's happening right now is the Nature Conservancy is working on their plan with the local communities, because they've got to come on side and support it. I'll be writing a memorandum of understanding between us. That'll be probably, with a little luck, get started this month. We'll get that in place. And right now, not a lot is being done this month, mostly because the Nature Conservancy just launched their beginning of the month, and I was able to attend that function. It's a major funding push for them in order to be able to go out and purchase a lot more land for Canada's 150th anniversary next year. So there is a lot of potential here. This would be the first in Manitoba. Tim has been working with Spruce Woods to try and get a dark sky preserve. So when you're working with the government, it takes a lot longer to do anything, whereas I think with the Nature Conservancy, probably no later than next summer, we'll have this in place. So one of the, we would be the sponsoring body as far as moving forward with the Nature Conservancy. And what we're hoping to do, one of the things that we would end up, our commitment to the project would be public outreach. So once or twice a year, we, the Winnipeg group, would be putting on public star parties there. And ideally what would happen, either after the star party or on another time, we would stay and be able to take advantage of the dark skies there. And the beauty of the place is there, whether it's cold weather or not, they have bedrooms there, they have cooking facilities there, they have washrooms there. So it's really, really a lot of great things that can happen for us to look forward. If we want to talk about pie in the sky kind of thing, we looked around a little bit when we were there last time, and Jerry wandered around and thought, well, we put an observatory. So there's potential for all these things moving forward, because again, the observatory can be part of the public outreach. So there's a lot of potential for this. They are really, really nice dark skies. And for the most part in that area, other than which direction was it? Did the trees move here? They don't really block out the sky though. But generally speaking, you have horizon, right, you have sky down to the horizon. So like earlier when Brian was talking about the planets are down along the horizon, well there you can actually get a good view of those planets from that site. So a lot of potential. We'll try to get updates as we move forward. So that's really where we're at in the process. Very positive. The nice thing about the Nature Conservancy, they just finished last year getting a dark sky reserve in Saskatchewan on one of their properties. So they're familiar with it at the national level. So they're fully supportive of this. It's just a matter of moving through the process with the RASC to make it happen. Any questions? Great. Thank you very much.
Thanks, Dennis. One thing to think about, of course, is someday we're going to get the 4th or 5th flood in our observatory out in Glenley. We could probably think about moving the observatory to this dark sky site. Leave the warm room, leave the observing pad there so it's close in, but maybe take the club's observatory, put a better mounting on it so that people could do photography as well as visual use and so on. Not something I'll lead as president, but certainly in the long-term thinking we've had is that a site like the one at Tolstoy, especially with the cooperation we're getting from the Nature Conservancy, essentially opening up the house there for our use as long as we put in our dues and do the public star party as well. Something to think about for the future anyway. I think going to work out really well for us if we don't drop the ball on this. So thanks very much, Dennis, for looking after this and going forward with it. Well, it's time for our break, and you'll notice we're going to be raffling off a few things down here. We're going to give you each 5 tickets.
Well, we all know Andrea, ex-president. So she's coming to us from a different point of view. Going to space instead of just looking at it. So here she is to tell you how you do it.
Can everyone, hear me in the back? Is this okay? Great, perfect. Yeah, so my name is Andrea. I'm also here with us today, which is Hollywood. Student at Maple Collegiate High School and student here at University of Vancouver. So yes, I also teach at Maple Collegiate High School. I'm a physics teacher there, and science and astronomy as well. And I'm here to talk to you about the Global Space Balloon Challenge and some of the science adventures that we've gone on. So this particular adventure, before I say anything else though, any students you see in the pictures here, to the whole thing in videos, the outside media release form. So this got started about 2 years ago. I'm also a member of MAPT, the Manitoba Association of Physics Teachers. It's a pretty kind of a small group of physics teachers. We meet once a month, and 2 years ago, one of the physics teachers who still kind of teaches a little bit at Chatsbury High School, Streamer, said, hey guys, I have a very great idea. Well, I want to kind of pass on all the cool stuff ISS before and astronauts on it. Very cool stuff. They wanted to kind of pass on their knowledge for kind of baby steps to this global space program. And all this there, and he's, okay, great, yeah, we'll do this, well. So, yeah, page 10 up. Sure. Okay. Instead of just telling you about the Global Space Balloon Challenge, I'm going to show you their promotional video. I heard it first. Let's see if this works.
Oops. Nice picture of this umbrella.
Okay, let's see. When I get this back. How do you do
Press
that?
F5.
Oh, you were good. Let's see, let's start this again.
Did you see it on your screen?
It worked before the break, I swear. That's okay. Okay, this is the, hopefully this will work. Chris?
What did you do?
Hands in the air.
Yeah, the sounds before, but I don't know.
Everything is connected.
Are you still plugged in?
Try it in Windows Media Player.
I'll try this. Nothing else failed for the force.
No, but we're not getting a sound even through the computer. Like on the computer speakers, there's no sound coming out of the computer speakers. So.
Okay, that's all right. What we'll do is, all right, besides this video here, which showed a bit, I can try to. All right, we'll move on. So, sorry about that. Everything worked before the break was square. Okay, this is my Physics 40S class a couple years ago, getting involved with this. And the first time we ever did it, I decided we had no clue what we were really doing. We just kind of dove into this head first and went, what are we going to do? So, to make sure I actually had students who were thoroughly interested in this, we started to build a payload, and I did it with my students in my 40S class. This is my senior class here. I don't have a ton of pictures of them building it. But one thing I did do, I had 28 students. This is a lot of students to deal with in the classroom. I'm trying to give something everybody to do in this endeavor here. So what I did was make a little kind of team names. We did the payload building team, the experiment team, the photography and video team, and communications media. So everybody kind of signed up for something in class, and they got to work in building this particular payload. This is the payload they came up with. Every payload is different. Everybody has its design. Every school had to keep the design too. So this was ours, our endeavor. The day of the launch. So the day of the launch came sooner than we thought. We started this in February of 2015 when we did this, and we launched in April. So we did not have a lot of time to meet and build and try to construct this for the first time. But we made it somehow to this to Morning Collegiate High School. I'm going to talk more about launching the balloons later on. And if you do have questions, feel free to just throw up your hand and ask questions. So on the day of the launch, there's a lot of little pieces involved with this particular launch. There's so many little details that we didn't even consider. That this was a huge learning curve for all of us. So the day of launch, we compiled this from raw air. This is from the last launch, 2016. So we constructed the launch like a NASA checklist. So we had one student checking off everything we had to do, and we had another student double checking what they had to do. And that's a picture of their checklist going through it. This is the picture of our students who are going through, making sure we have everything inside the payload that we need to have in them. This is just more pictures of laying out. So we have to do it in order to launch this thing, because we're building a really big balloon here. So we need nothing to touch the balloon. This is one sample left over of our balloon here. It's a latex balloon. So this particular balloon, you can't even touch it with your hands. It has oil on your hands, can you damage it. If you accidentally nick it with your fingernails, you're toast. Whether grass touches it, or pretty much if anything rips tears go near it, you're not going to have you're not going to have a successful launch. So hence why we have these big outstretched platforms here, the big tarps. In order to launch this other balloon, we need a lot of other equipment inside. So you'll hear more about that later on. One thing we did get, of course we need for a big weather balloon, is helium. So this is the first time we had a big helium tank out here in the field. I'm going to transfer this thing over. We had to makeshift this particular design here. This was PVC piping, different connectors to the tube. And the day of the launch, even though we had practiced the launch, we built our payload, we had our cameras ready, we had the GPS launch ready. everything that could go wrong does go wrong. It did go wrong on the launch.
There are a lot of things that could go wrong. You just have to know really bad.
So all the little things went wrong first. We sort of did this part here, and all of a sudden, within this little cord inside our lovely, this part here actually spun a leak. Yeah, helium's not cheap, and we're starting to blow up this big balloon, and we're hanging on to it, and then we hear this. And it's an endangered element right now, and all we hear is duct tape to the rescue, exactly. So we duct taped the heck out of that thing. And then we put our balloon on. Notice that all the students here, they're also holding latex gloves, which you don't want to get in your hands on near the balloon. So they're trying to lay out the balloon. We have the hose, we get everything hooked up, the helium, and the payload's ready. Here it is here now. You'll notice in this picture, only one person is hanging on to the balloon. This is not really.
It also be mentioned that you have like, there's only Robin's thumb, so he didn't exactly have the ideal grip on the neck of the balloon. So you can kind of see where this is going. But Jasper had our back. They have a spare balloon, which they're so kindly to give to us.
It was too funny. If you look really closely on the next slide, you'll see little $10 bills falling out of that balloon. That was our entire tank of helium, our entire balloon, the whole $300 was gone.
It's not cheap.
And for this one, what was really interesting on the field here, the students always have this mentality when they get on the field, it's a competition. Oh, there's GC over there. Look at GC. Our payload's better than yours. I mean, what a, the kind of student competition. But all of a sudden, when stuff hits the fan here, you want to do this together, and the students came together in camaraderie. Says Shasbury came to our rescue, being the school that had the most injured. So Shasbury, yes, they gave us a new balloon, and our helium tank's empty. So all of a sudden, every school, one of the big trucks came around, where the teachers grabbed the truck and took every helium tank around for us. There were 4 other schools, including us, involved. And every helium tank came around, and we signed off the rest of the other helium to fill this balloon. This is us at the very end here. Pointing out.
Well, not the very end. End of like launching. This is only the beginning of the journey.
One of my students, I think, took this picture. And the next part of the journey is Holly.
All right, so next comes the big chase. So this one's decently difficult because other schools, they have radio licenses and they have GPS trackers that they can track their radios, but we didn't. We used our phones. And in southern Manitoba, if you live there, you know that signal isn't the greatest, so we often lost our signal and had no idea where to go. But thankfully, with the help of Shaftesbury, I think, their radios, they helped us locate a balloon. So we're driving around for hours trying to locate where a balloon landed. Or maybe wondering if it landed in the States. Who knows?
We could, so we did have a GPS in here, but Shaftesbury High School had 5 radio licenses, so just enough to go around. Because if you're launching a 12-kilogram balloon, which is like this big, when you fill up on the ground, it's going to expand to 10 meters across, 20 meters across. When it hits the upper atmosphere, you can't send it up just willy-nilly. You need to be able to have a way to track this thing through the atmosphere. So we had their license attached to the GPS inside, and all our proper antennas. And the problem is halfway through, so there's cell phones died out, but
It's basically on our GPS tracker, like on the map, it showed approximately like where the last like thing of the signal went, then all of a sudden it just went dead. And it's like didn't show like any sort of like velocity of like where it was going. So we're just like, oh, it's approximately over here. Let's look over here. And that's not exactly the best way because
you can't find it.
especially when there's tons of open fields and properties you have to cross in order to look, going through barbed fences.
And we discovered that these fields, that it would be so easy to find, is this little blue box. It became a needle in a haystack very quickly in the middle of the vast field. 3 hours later with binoculars and our gas tanks running low. It was not working. But Shaftesbury High School, because they have radio licenses, they have antennas on the back of their cars that can track. Our GPS didn't die. It landed, but it stopped pinging a signal to other satellites to ping a signal back to the internet so they could check it on our phones. They have radio licenses that can detect the signal at line of sight. We don't have that. So Shaftesbury, we were able to find your payload and have your students.
Smartphones only get you so far.
And one of our students told me at the end of the first one there, he said, an experienced sailor never learned on combs he uses. But here's the cool part. Once we got these shots back from our first, so this balloon went up 33 kilometers into the atmosphere. It's 140,000 feet. This is well beyond WestJet. It's making WestJet Air Canada goodbye, and it's going up higher. So you can just start to see a little bit of the curvature of the Earth. Very excited to see these types of pictures and video, and you kind of, then it really hits home. We put this there, we put this in space. Seriously, in space. The slide of the halfway up to the atmosphere. This is how we were able to launch the balloon. So you can't, this is a really bad predictor. Anyone know why?
Airport.
Airport, excellent. Yeah, this is the airport right here in Winnipeg. This is, if you go to havehub.org, they have a flight predictor. So you have to type in all your information, your latitude, longitude, date of launch, time of the launch, your ascent rate, how fast your balloon will rise, and the burst altitude. Because the balloon has so much helium, and the latex gets stretched pretty thin, so eventually it will burst, and you want it to burst. If it doesn't burst, that leads to the force burst. And then these set right here. So it shows you, if you launched here, the balloon usually goes into a classic S. It'll burst and then come back down right inside the airport. So we can't launch here. But this is this predictor, you can only predict it to about 72 hours before the launch. So that's always fun, but permission comes. 48 hours before the launch, we officially decide where to go. You have to go at least where there are bathroom facilities, and usually go to other schools to get them involved for next year.
Basically where there's civilization.
This is just other technical stuff I threw in here. So we didn't just do this willy-nilly. We did do our homework and talk about gas and helium. These are preset things that we took so we could estimate our burst altitude where we were going. I put up this slide here just to show. This was the website, aprs.fi. This was the website our student was going to with their smartphones, trying to track the balloons. So anyone around the world, if you had our particular call sign, type in the call sign here, it'll be for the Shaftesbury High School -5, and you would track the balloons. You can actually track all little little red dots here, pings from the GPS telling you on a pocket of information. And those pockets tell you the altitude and fast. This was our track. You can get this from Google Earth from the website here. It kind of shows where we launched. It goes up the balloon at first, and we'll explain what happens here.
When it falls very fast. All I can give you. And our parachute didn't quite work, except the this was somehow built well enough so it remained in one piece, which is pretty sweet. Shout out to the 2015 grade 12 students.
This did not fall apart. What did fall apart was the balloon was up here, then you had the parachute lines down to your payload. When the balloon burst, it came around, ripped off some of the fishing lines things here. Just notice there's two missing. Yeah, it really tore the fishing line off. You can see the red glare of the parachute, and there's no parachute. It's kind of free falling off 3 kilometers into the atmosphere.
How long was the flight?
About 2 hours.
It just speeds up, slows down, speeds up, slows down, and
But this is why you want to launch way outside of Winnipeg. You want to launch this in a populated area so there are safety concerns.
then what if our parachute, I don't know, landed in traffic or God knows where?
You remember the kind of things that we went for mechanical property, what the eyepieces, nor, it was an eyepiece which
Does that predictor, I mean, if you were to think about it, I wouldn't imagine that it would, go out, come back. I guess was it just different levels of wind traveling?
Once you get into the stratospheric winds, you get quite different directions than down
Yeah, because when we're tracking, it shows how fast it's going and what altitude is. So at certain altitudes, it would be going at like maybe 70 kilometers, and then all of a sudden it would slow down to like maybe 30 or 50. Pick up again, slow down.
Just to show you an idea of what the atmosphere here. So you always like to get students that are going to space. Stratosphere. You're going above the level of the stratosphere. Your space is. So that's how far our influence really goes.
Close enough to space.
Okay. There is a video.
Hey, Naples! 5, 4, 3, 2, 1, liftoff!
discussion comes up again, do you want to try this again? And all of us physics teachers, we say, yeah, we want to try it again. Because now we had jumped over the big learning curve, we were ready for the second challenge. Our students got together and designed the mission patch in there. And so the middle zone was one student's design, and then my coworker had designed this patch here for the front. So this is out. And this year we called ourselves Maraude Air, and they're Marauders, I think, basically.
And we consisted of our science club instead of her physics class.
Just for a little background, to do this particular balloon challenge is about $1,000 a launch, depending on the price. This year, I got funding the first year from my principal because I kept it in my physics class. But the second year we didn't in the classroom. It was students all over the school welcome to come and join. And in Garden City, down here, their video got shown at a board meeting at Seventh School Division, and the division said, wow, this is cool. Make it happen again. And they actually gave us quite a bit of funding to do it for school. So I thought, well, maybe we should take this a little more seriously.
Me and Miss Meisner enrolled in a amateur radio course. She succeeded, but unfortunately I didn't quite make the cut. But I'm procrastinating studying and eventually maybe getting a radio license. But you know, university has lots of courses, so the best time for that right now.
It was an insane amount of work. I had no idea. I thought, I'm put it back on. I should do this.
9 to 3 on a Saturday. That's fun.
Saturdays.
A lot of studying too.
Yeah. The book was not thin. It was like this thick, and I thought, okay, I got this. No, I had maybe 2 chapters at best, and all the rest I'm like, I don't know what this is.
Yeah, a lot of the stuff wasn't exactly clear.
It was, so there are 2 radio licenses. You can get the basic and the advanced.
There's also the basic with honors for those who get 80% or more on their exam or test.
It doesn't matter. We got a license. Moving on.
License, you're good to go because you don't need all those different frequencies to operate on.
So we got our radio license. Just to show you, this was the cool Yaesu because we had a lot of funding, so we got to buy really cool toys.
Our very sick setup.
Setup on the back. This is on my garden picture, but this was pretty much the setup here with the big antenna. So we felt super awesome with this big floppy antenna on the back of the car and our radio license and our new Yaesu that pings out a signal so it can actually track. It collected the packet from our GPS inside our payload.
So we could track our balloon with more accuracy. Not have to drive around for hours.
So this is some students. We're figuring out the GPS. Because this particular contraption here has to talk to the Yaesu in the car. We get that to work. This took some fiddling around. A lot of things. We decided to go one step further with our experiments, because before, when you are involved in the Global Space Balloon Challenge, if you want to launch, you're going to need cameras. So we had cameras in the first one, but we decided to go and step it up a bit to do Arduino programming. So,
if you have any questions about what Arduino is, we do not know how it works. Other students were responsible for the Arduino, and another teacher for programming it and analyzing all this data and stuff. We have nothing to do with it, so if you have any questions, you are out of luck.
one of the hardest things as being an educator from my perspective was trying to let go of wanting to be one step ahead of the students all the time and try to help them out any way you can. And in this case, I had to go.
Not our team.
But it's okay, because the students were amazing, and they saw it and put this together and figured it out by looking to other coworkers. And this is the building of the payload.
The part where I boss around a lot of underclassmen.
So payload here on the other students. This is what the balloon kind of looks like, the picture on the diagram here. So we have the balloon here, why we use feet. Parachute shoot, and we put this in for extra stabilization. We try to keep it from spinning. We use new fishing lines this time around. This is the kids here working of the fishing line devices here. This is our new way of trying to create stabilization within the. You notice in the other videos are kind of like, the world looks slanted.
So you don't get nauseous while watching the footage.
Next video, this was a bit of a stretcher here. We're all quite nervous. This is global space to do this too. Only 3 days. We had our crazy checklist. This was a picture inside the payload. The weight of the payload means a lot too. Maximum weight 1.5 kilograms. Beyond that, if you have it too heavy or too light, you risk.
You will see what happens when it's too heavy.
It's better to have it too heavy, we discovered, than too light. If it's too light, you can end up with international stories that you may not know.
It's a great dinner conversation.
So day of the lunch, we had an absolutely perfect day on Carbon Collegiate High School. Like weather-wise, it was beautiful. This is all the students laying over the tarps, getting ready, and this time around it was a lot different. The students had worked so hard, they had everything just down to a T. So for educators' perspective, this one.
And also it's great because since it was club organized and not like in-class curriculum, it means that the students who are working on it really want to work on it, otherwise they wouldn't join the team.
Here. Just to get a sense of scale, this was interesting.
So this is what we want to put in our balloon as our astronauts. We have featured here photos of Nintendo scientists, Sigmund Freud action figure, a necklace, some aliens, Lego Man, other pieces of paper. Paper made it, but astronauts unfortunately were too big. Yes.
There was the debate of, hey, you want to put all this cool stuff?
Oh yeah.
Personalized, this stuff is ours, and it goes off to space. Like, how cool to say, this went up to the edge of our atmosphere into space.
Also, not pictured, there's also a muffin we want to put in there, which we could say we went to space and ate it, hopefully not the cancer from all the radiation. Unfortunately, the cancer muffin did not make it to space.
This is what they did when we were not looking. And the discussion came up was, what happens if we don't get it back? Don't put anything valuable when you want back. Just in case. So this is a few more pictures of us designing the balloon here, just to give you an idea, because we're going to show you a bit of a challenge that happened here. Take note of this part here. This is part of the balloon. We have successfully duct taped this thing up. So the big hose comes out here, and once you're done filling it, you have to fold it up, duct tape it, and there's wire, there's string, there's zip tie to make sure this thing doesn't fly away. We have a lot. So just take a look at the complexity there. There's a reason why. And just a kind of a note here, this stuff does not happen on its own. We have a lot of help from coworkers. You might not see in the background of the pictures. Or kind of some people from last year. These are my two science students here. More than people. These were the individuals. There's nice remaining video that you're watching. There's a lot of the video process.
Work on the Arduino and all the computer stuff that we have no idea how it works.
And the other people over there.
That's scary. He released the balloon the first time.
So if it wasn't for these coworkers and the dedication of them, nothing like this actually goes on. So it doesn't happen in isolation. We have to show you, because our video doesn't really show it, the nice video that we have. So we thought we'd explain to you the challenges, because one of the ideas of working with science like this, hands-on projects, that it doesn't always go the way you want it to. We learned this from the first part, the helium balloon linking, losing the balloon, things don't always go the way you want them to.
Each year there are different challenges. Not everything goes right in one. Like something may go right the first year, a different thing might go wrong. Here we're pay close attention to our reactions. Took us a moment to kind of register the situation.
So at this point, besides my blood sugar hitting the center of the earth, we had to take down the balloon, dismantle that picture I showed you with the duct tape and everything else, without destroying and tearing the balloon. Because if we tear this balloon, if one thing happens to it, it's game over.
Well, except we had a spare balloon. Except, remember what happened last year, or 2015, and how Shaftesbury was oh so kind to give us their spare balloon? Well, last year, their balloon ended up going bye-bye. So we had a spare balloon, which we gave back to them, so the debt has been paid off between us.
And you saw that camaraderie come again here. So we were, with Shaftesbury lost their balloon this launch, we ran over, helped them, and as soon as this happened to us, they ran over and helped us prepare the, shows it towards the end here. And then the chase was on. Yeah, so this was a particular chase here. We had to go back down kind of the side roads of the southern parts of Manitoba here to find the balloon. Now this was the tricky part, because we had our radio licenses. We even bought a spot tracker. We didn't buy, we rented. It was rented from Wilderness Supply. A spot tracker in there, and I gave the website address to one friend and said, if anything shall happen to this balloon, tell me where it is, just in case.
Always
have a backup plan. And sure enough, halfway through, so about an hour, we get it up there, it launches, we're like, we got this. I'm on with the Yesu, I'm next door to the subway, and the signal stops. We're not getting anything from the balloon. All those months that it's studying for the flight. And eventually, after about an hour, we got one signal aimed back to us on our little Yesu.
Joy.
So we were able to track it down. We're on the side of the road there. What I had to do was take the coordinates from the Yesu, because it actually spits out a longitude, latitude. I pulled out my GPS, a little Garmin, typed in the exact coordinates. Your destination is 500 meters to the right.
Recalculating.
And this is all of us. So the kids ran. We parked off to the side of the road first.
Running dusty conditions does not feel good.
It looked really soft there. It's not. It's so soft.
Lots of mud and dust. It's just wonderful.
This was the first time that Shaftesbury High School and all high schools actually saw the balloons come down. So this was a kind of a milestone in the global space pollution last year. So this was pretty amazing that we saw all the balloons on. We got to see them. So this is our opening of the payload here.
Our parachute route this year. So both our boxes were in one piece.
Oh no, we didn't tell them why the box stopped.
Well, once again, the muffin didn't go in the box because it's too heavy.
As soon as you turn your head, the students are like, we're going to radiate this muffin. So the joke was that I went to Tim Hortons, bought all these muffins. muffins and coffee and donuts to the kids. They stuffed one of the muffins inside the payload. And Jasper ran over and said, "You need to take a mass of the payload. We tear over the payload. Here's just this muffin."
Well, told us we could put it in the payload. The chapter was cheering us on.
Shafter did not tell us, so we tear open, and there was a big joke about how these muffins are so young, so they ruin science.
Hortons can sponsor us next year.
Never know. This was our launch from this year here, just to show you. So our GPS completely crapped out at some point that we don't know why. We asked amateur radios who were there to help us out as well. They had no explanation.
Technology. And here's our remains from last year. So once again, part of the balloon, the oh-so-tangled stabilizers, and our parachute that actually works.
So this was the launch here at Carmen. The GPS craps out, and then there's this signal here, and my heart jumps with joy, and this is the last signal down here where we were actually able to retrieve those. So this is just another view of the weirdness that happens within launch. Only Maple Street is this. We thought it was hilarious that this little tiny bump right here. See it down.
You know what happened there. Also, more technical errors with that, considering footage.
I want to show you a few slides of the images we did get back. Because we had better technology. We had neutrinos, we had our GPS unit back in there, and we also had
HD cameras also. We had better quality cameras, so we'd get less fuzzy pictures.
just to show you an idea at the time. So we had one camera pointing straight down, one pointing straight up. And this will show you the growth of the balloon as it hits the upper atmosphere. So this is just a launch over time, and this is just about the balloon burst here. And we realized we needed external batteries.
Well, it would have if it wasn't for that little mishap. Because what happened was when the balloon came down, a lot of time elapsed between the failure of the first launch and the success of the second launch. So the batteries in the good camera unfortunately ran out. So we couldn't get all of the footage we wanted to. Sad face.
But we were successful in getting a lot of great videos, and we had enough money left over that for next year we got a GoPro. Okay, I will. There were two more slides down here. This is our review of the series.
going to have VAOV.
Seen any signs of a phone call to air traffic control before you launch it?
I left that in the hands of the very experienced Mr. Bob Streamer, professor at high school. The deal is, if we had 12 kilogram balloon, that was one of our first questions. They said you don't have to have your phone, it's 1,200 kilograms. You cannot launch near any airports. You have a 1,600 kilogram balloon, you need to permit.
Any other questions?
Yeah, how did all the other balloons fare when they were all launched together then? Did they all come down to the same place? Did they go to the same height? What was the story there?
All the balloons, just about. They all pretty much went to the same height and pretty much came down within the same area. It might have been off by a little bit, a few meters, but we were very close to each other.
Adam?
Yeah, this is a really a mind-blowing project. Like, that is so cool that you were able to pull that off. And to see the curvature of the Earth, too, is really, I don't know, it's just mind-blowing. It's unreal. Now that you have your radio license, are you going to be starting a ham club?
30 is a ham club.
Is it really?
Yeah, they meet at Shaftesbury. I forget where.
Well, congratulations. I mean, that's really something. It's amazing.
We lost the first balloon the second time around. Like the first time we lost it, so the second time around we're supposed to do a lift test. And we had the proper thing to, if the deal is, if it lifts a 1 kilogram jug of water off, you're good. But we were hanging on to it, and we duct taped the balloon to our PVC pipe just to start. But we were kind of hanging on to it when we did it, so our calculations, that's because, just because of that handheld we were doing, we didn't put enough helium into it, so we actually ended up having to take it apart and pump more balloons.
And those are astronauts.
Are the YouTube videos available from this site as well?
Yes, our video is up on YouTube, but you might have to go to this website here to get it. But if you Google it on YouTube.
And also, did you mention that you can't use any larger balloon with a license?
We can use 1,200 gram balloons with a radio license. If you use a 1,600 gram balloon, you need a permit to launch it. This was the highest, the biggest balloon we could get within our range of safety.
For extra challenge, you could try a night launch with LEDs on it, you know? Then you're really putting faith in the AC.
We would love to do it. We talked about doing a night launch with cross our fingers on the world. That would be this hot. Yeah. Any other questions?
You put in a certain amount of helium to hold the balloon at a certain level, let's say 110,000 feet for like 6 hours.
Sorry?
Let's say if you put enough helium, so just hover at, let's say, 110,000 feet for 6 hours, and then come down, or would it go too far?
Probably could. We don't want it to do that.
We only have so much time as students because, well, we got to get permission in order to go, and if we're out all day, that might be problematic for other students' schedules.
We do that in Antarctica, but you have to have venting system because it warms up during the day and cools at night and sinks, so you actually have to carry a little extra with you or dump ballast to keep it at a constant altitude. It's also a pressurized balloon more than this kind of balloon. Okay, we're done. Thank you very much. Up at night with a little telescope. So he's coming to us from a different point of view. Going to space instead of just looking at it. So here he is to tell you how you do it.
Can everyone, hear me in the back? Is this okay? Okay, perfect. Yeah, so my name is Andrea. I'm also here with us today. This is Holly Lee, past student at Maple Collegiate High School and now student here at University of Manitoba. So yes, I also teach at Maple Collegiate High School. I'm a physics teacher there, and science and astronomy as well. And I'm here to talk to you about the Global Space Balloon Challenge and some of the science adventures that we've gone on. So this particular adventure, before I say anything else though, any students you see in the pictures here, go through the whole thing in videos, they all send me a release form. So this got started about 2 years ago. I'm also a member of MAPT, the Manitoba Association of Physics Teachers. It's a pretty kind of a small group of physics teachers. We meet once a month, and 2 years ago, one of the physics teachers who still kind of teaches a little bit at Chatsbury High School, streamer, said, hey guys, I have a really great idea. Music fire scenes, but I want to kind of pass on all the cool stuff I've been doing at my school, which is launching balloons, and they are heavy into amateur radio. They've talked to the ISS before, and astronauts on it. Very cool stuff. They wanted to kind of pass on their knowledge, so kind of baby step us through this global space balloon. And all of us there, and he's, okay, great, yeah, we'll do this, Rob. So, sure. Okay. Instead of just telling you about the Global Space Balloon Challenge, I'm going to show you their promotional video. I've heard it first. Okay, when I get this back. How do you get it
Press
back?
F5.
Oh, you were. All right. Let's see. Let's start this again.
Do you see it on your screen?
It worked before the first square. That's okay. Okay. This is the. Hopefully this will work. Chris?
What did you do?
Hands in the air!
Yeah, the sounds before, but I don't know. Everything is connected.
Are you still plugged in?
Try it in Windows Media.
try this. Nothing else failed for the horse.
No, but we're not getting a sound even through the computer. Like when I hear the speakers, there's no sound coming out of the computer speakers. So. No, we tried. There's nothing coming out of the
Okay, that's all right. What we'll do is, all right, besides this video here, which showed a bit, I can try to. All right, we'll move on. So, sorry about that. Everything worked before the break is square. Okay, this is my Physics 40S class a couple of years ago, getting involved with this, and the first time we ever did it, I decided we had no clue what we were really doing. We just kind of dove into this head first and went, what do we do? So, to make sure I actually had students who were thoroughly interested in this, we started to build a payload, and I did it with my students in my 40S class. This is my senior class here. I don't have a ton of pictures of them building it. But one thing I did do, I had 28 students. This is a lot of students to deal with in the classroom. I'm trying to give something everybody to do in this endeavor here. So what I did was make a little kind of team games. We did the payload building team, the experiment team, the photography and video team, and communications media. So everybody kind of signed up for something in class. And they got to work in building this particular payload. This is the payload they came up with. Every payload is different. Everybody had to design. Every school had to keep the design too. So this was ours, our endeavor. The day of the launch. So the day of the launch came sooner than we thought. We started this in February 2015. We did this, and we launched in April. So we did not have a lot of time to meet and build and try to construct this for the first time. But we made it somehow to this to Morning Collegiate High School. I'm going to talk more about launching the balloons later on. And if you do have questions, feel free to just throw up your hand and ask questions. So on the day of the launch, there's a lot of little pieces involved with this particular launch. There's so many little details that we didn't even consider. That this was a huge learning curve for all of us. So the day of launch, we compiled this from raw air. This is from the last launch, 2016. So we constructed the launch like a NASA checklist. So we had one student checking off everything we had to do, and we had another student double checking what they had to do. And that's a picture of their checklist going through it. This is the picture of our students who are going through, making sure we have everything inside the payload that we need to have in them. This is just more pictures of laying out. So what you have to do in order to launch this thing is we're building a really big balloon here. So we need like nothing to touch the balloon. This is one sample left over of our balloon here. It's a latex balloon. So this particular balloon, you can't even touch it with your hands. It has oil on your hands, can damage it. If you accidentally nick it with your fingernails, your toast, the blade of grass touches it, it's over. Pretty much. If anything rips tears goes near it, you're not going to have a game over. You're not going to have a successful launch. So hence why we have these big outstretched platforms here, the big tarps. In order to launch this other balloon, we need a lot of other equipment inside. So you'll hear more about that later on. One thing we did get, of course we need for a big weather balloon, is helium. So this is the first time we had a big helium tank out here in the field. I'm going to transfer this thing over. We had to makeshift this particular design here. This was PVC piping, sugar connectors to the tube. And the day of the launch, even though we had practiced the launch, we built our payload, we had our cameras ready, we had the GPS launch ready. Everything that could go wrong does go wrong. It did go wrong on the launch.
There are a lot of things that could go wrong. You just have to know really bad.
So all the little things went wrong first. We sort of did this part here, and all of a sudden, within this little cord inside our lovely, sit under. This part here actually spun a leak. Yeah. Helium's not cheap. And we're starting to blow up this big balloon, and we're hanging on to it. Then we hear this. No. And it's an endangered element right now, and all we hear is. Duct tape to the rescue, exactly. So we duct taped the heck out of that thing. And then we put our balloon on. Notice that all the students here, they're also holding latex gloves. You don't want to get your hands on near the balloon. So they're trying to lay out the balloon. We have the hose. We get everything hooked up, the helium, and the payload's ready. Here it is here now. You'll notice in this picture, only one person is hanging on to the balloon. This is a really big
It also be mentioned that you have like there's a rocket's thumb, so he didn't exactly have the ideal grip on the neck of the balloon. So you can kind of see where this is going. But that's where you have it back. They have a spare balloon, which they're so kindly to give to us.
It was too funny. If you look really closely on the next slide, you'll see those kind of bills falling out of there. That was our entire tank of helium, our entire balloon, the whole $300 is gone.
It's not cheap.
And for this one, what was really interesting on the field here, the students always have this mentality when they get on the field, it's a competition. Oh, there's GC over there. Look at GC. Our payload's better than yours. I mean, what the kind of student competition. But all of a sudden, when stuff hits the fan here, you want to do this together, and the students came together in camaraderie. Says Shasbury came to our rescue being the school that had the most injured. So Shasbury has gave us a new balloon, and our helium tank's empty. So all of a sudden, every school, one of the big trucks came around, where the teachers grabbed the truck and took every helium tank around for us. So there were 4 other schools, including us, involved. And every helium tank came around, and we siphoned out the rest of the other helium to fill this balloon. This is us at the very end here. Cleaning up.
Well, not the very end. End of like launching. This is only the beginning of the journey.
One of my students, I think it was you who took this picture. And the next part of the journey, so
All right, so next comes the big chase. So this one's decently difficult because other schools, they have radio licenses and they have GPS trackers that they can track their radios, but we didn't. We used our phones. And in southern Manitoba, if you live there, you know that signal isn't the greatest, so we often lost our signal and had no idea where to go. But thankfully, with the help of Shaftesbury, I think, their like radios, they helped us locate a balloon. So we're driving around for hours trying to locate where a balloon landed. Or maybe wondering if it landed in the States, who knows?
We didn't have a GPS in here, but Shaftesbury High School had 5 radio licenses, so just enough to go around. Because if you're launching a 12-kilogram balloon, which is like this big, when you fill up on the ground, it's going to expand to 10 meters across, 20 meters across. When it hits the upper atmosphere, you can't send it up just willy-nilly. You need to be able to have a way to track this thing through the atmosphere. So we had their license attached to the GPS inside, our proper antennas. And the problem is halfway through, somewhere there's our cell phone's not out, but
Basically on our GPS tracker, like on the map, it showed approximately like where the last like thing of the signal went, then all of a sudden it just went dead. And it's like didn't show like any sort of like velocity of like where it was going. So we're just like, oh, it's approximately over here. Let's look over here. And that's not exactly the best way because you can't find it. Especially when there's tons of open fields and properties you have to cross in order to look through farm fences.
And we discovered that these fields, that was going to be so easy to find, is this little blue box. It became a needle in a haystack very quickly in the middle of the vast field. 3 hours later, with binoculars and our gas tanks running low, it was not working. But Shaftesbury High School, because they have radio licenses, they have antennas on the back of their cars that can track. Our GPS didn't die. It landed, but it stopped pinging the signal to other satellites to ping a signal back to the internet so they can check it on our phones. They have radio licenses that can detect the signal at line of sight. We don't have that. So Shaftesbury will be able to find your payload and have your students.
Smartphones only get you so far.
And one of our students told me at the end of the first one there, he said, an experienced sailor never learned on calls he uses. But here's the cool part. Once we got these shots back from our first, so this balloon went up 33 kilometers into the atmosphere. It's 140,000 feet. This is well beyond WestJet. It's making WestJet Air Canada goodbye, and it's going up higher. So you can just start to see a little bit of the curvature of the Earth. Very excited to see these types of pictures and video, and you kind of, then it really hits home. Like, we put this there, we put this in space. The sight of the halfway up to the atmosphere. This is how we were able to launch the balloon. So you can't. This is a really bad predictor. Anyone know why?
Airport.
Airport, excellent. Yeah, this is the airport right here in Winnipeg. This is, if you go to havehub.org, they have a flight predictor. So you have to type in all your information, your latitude, longitude, day of launch, time of the launch, your ascent rate, how fast your balloon will rise, and the burst altitude. Because the balloon has so much helium, and the latex gets stretched pretty thin, so eventually it will burst, and you want it to burst. If it doesn't burst, that leads into worse burst. And then these right here. So it shows you, if you're launched here, the balloon usually goes into a classic S. It'll burst and then come back down right inside the airport. So we can't launch here. This is this predictor, you can only predict it to about 72 hours before the launch. So that's always fun, but permission comes. 48 hours before the launch, we officially decide where to go. You have to go at least where there are bathroom facilities, and usually go to schools to get them involved for next year.
Basically where there's civilization.
This is just other technical stuff I threw in here. So we didn't just do this willy-nilly. We did do our homework and talk about gas and helium. These are preset things that we took so we could estimate our burst altitude where we were going. I put up this slide here just to show This was the website, aprs.fi. This was the website where my student was going to with their smartphones, trying to track the balloons. So anyone around the world, if you had our particular call sign, type in the call sign here, it'll be for the SHS, Statutory High School -5, and you would track the balloons. You can actually track all little red dots here, pings from the GPS telling you pockets of information. And those pockets tell you the altitude and facts. This is our track. So you can get this from Google Earth, from the website here. It kind of shows where we launched. It goes up the balloon at first, and we'll explain what happens here.
When it falls very fast. All I can give you. And our parachute didn't quite work, except this was somehow built well enough so it remained in one piece, which is pretty sweet. Shout out to the 2015 grade 12 students.
This did not fall apart. What did fall apart was the balloon was up here, then you had the parachute lines down to your payload. When the balloon burst, it came around, ripped off some of the fishing lines things here. Just look at the two missing. Yeah, it really tore the fishing line off. You can see the red glare of the parachute, and there's no parachute. It's free falling 3 kilometers into the atmosphere.
How long was the flight?
2 hours.
It just speeds up, slows down, speeds up, slows down,
But this is why you want to launch way outside of Winnipeg. You want to launch this in a populated area so there are safety concerns.
and what if our parachute, I don't know, landed in traffic or God knows where?
So I remember the kind of things that we went mechanical property, what the eyepieces. It was an eyepiece that talked about louder, which
Because that predictor, I mean, if you were to think about it, I wouldn't imagine that it would, go out, come back. I guess was it just different levels of wind traveling?
Once you get into the stratospheric winds, you get quite different directions than down in the
Yeah, because when we're tracking, it shows how fast it's going and what altitude is. So at certain altitudes, it'll be going at like maybe 70 kilometers, and then all of a sudden it'll slow down to like maybe 30 or 50. Pick up again, slow down.
Just to show you an idea of what the atmosphere is here. So you always like to get students that are going to space. Stratosphere. You're going above the level of the stratosphere. Your space is. So that's how far our influence really goes.
Close enough to space.
Okay. There is a video.
Okay, Naples. 5, 4, 3, 2, 1. Liftoff.
So the second year rolls around and the discussion comes up again. Do you want to try this again? And all of us physics teachers, we say, yeah, we want to try it again. Because now we had jumped over the big learning curve and we were ready for the second challenge. Our students got together and designed the mission patch in there. And so the middle zone was when students designed, and then my coworker kind of designed this patch here. So this is and this year we called ourselves Maraud Air. And they're Marauders, I think, basically.
And we consisted of our science club instead of her physics class.
Just for a little background, to do this particular balloon challenge is about $1,000 a launch, depending on the price. This year, I got funding the first year from my principal because I kept it within my physics class. But the second year we didn't in the classroom. It was different students all over the school who would come and join. And in Garden City, down here, their video got shown at a board meeting at 7 school division, and the division said, wow, this is cool. Make it happen again. And they actually gave us quite a bit of funding to do it for school. So I thought, well, maybe we should take this a little more seriously.
Miss Meisner enrolled in a amateur radio course. She succeeded, but unfortunately I didn't quite make the cut. But I'm procrastinating studying and eventually maybe getting a radio license. But you know, university has lots of courses, so who has time for that right now?
It was an insane amount of work. I had no idea. I thought, I'm put it back on. I should do this.
9 to 3 on a Saturday.
That's what Saturdays.
A lot of studying too.
Yeah, the book was not thin. It was like this big, and I thought, okay, I got this. No, I had like maybe 2 chapters at best, and all the rest I'm like, I don't know what this is.
Yeah, a lot of the stuff wasn't exactly clear.
It was, so there are 2 radio licenses. You can get the basic and the advanced.
There's also the basic with honors for those who get 80% or more on their exam or test.
It doesn't matter. We got a license. Moving on.
License, you're good to go because you don't need all those different frequencies to operate on.
So we got our radio license. Just to show you, this was the cool Yesu because we had a lot of funding, so we got to buy really cool toys.
Our very sick setup.
So that's on the back. This is on my card picture. But this was pretty much the setup here with the big antenna. So we felt super awesome with this big flappy antenna on the back of the car and our radio license and our new Yesu that pings out a signal so it can actually track. It collected the packet from our GPS inside our payload.
So we could track our moon with more accuracy. Not have to drive around for hours.
So this is some students, we were figuring out the GPS. This particular contraption here has to talk to the AC in the car. We need that to work. This took some fiddling around. A lot of things. We decided to go one step further with our experiments, because before, when you are involved in the Global Space Balloon Challenge, if you want to launch, you're going to need cameras. So we had cameras in the first one. We decided to go and step it up a bit to do Arduino programming. So.
If you have any questions about what Arduino is, we do not know how it works. Other students were responsible for the Arduino and another teacher for programming it and analyzing all this like data and stuff. We have nothing to do with it, so if you have any questions, you are out of luck.
One of the hardest things of being an educator, from my perspective, was trying to let go of wanting to be one step ahead of the students all the time and try to help them out every way you can. And in this case, I had to go. I don't know.
Not our field.
But it's okay, because the students were amazing, and they saw it and put this together and figured it out by over 3,000 coworkers. And this is the building of the payload.
The part where I boss around a lot of underclassmen.
It's the payload here on the other students. This is what the balloon kind of looks like, the picture on the diagram here. So we have the balloon here, I don't know why we use feet. Parachute, and we put this in for extra stabilization. We try to keep it from spinning. We use new fishing line this time around. This is the kids here working of the fishing line devices here. This is our new way of trying to create stabilization within the. You notice in the other videos are kind of like, the world looks slanted.
So you don't get nauseous while watching footage.
Next video, this was a bit of a stretcher because we were quite nervous. This is global space to do this too. Only 3 days to launch. We had our crazy checklist. This was a picture inside the payload. The weight of the payload means a lot too. Maximum weight 1.5 kilograms. Beyond that, if you have it too heavy or too light, you risk.
You will see what happens when it's too heavy.
It's better to have it too heavy, we discovered, than too light. If it's too light, you can end up with international stories that you may not want.
It's a great dinner conversation.
So day of the lunch, we had an absolutely perfect day on Carmen Collegiate High School. Like weather-wise, it was beautiful. This is all the students laying over the tarps, getting ready, and this time around it was a lot different. The students had worked so hard, they had everything just down. So for educators' perspective, this one.
And also it's great because since it's club organized and not like in class curriculum, it means that the students who are working on it really want to work on it, otherwise they wouldn't join the team.
Here. Just to get a sense of scale, this was interesting.
So this is what we want to put in our balloon as our astronauts. We have featured here photos of the scientists, Sigmund Freud action figure, a necklace, some aliens in Lego Man, other pieces of paper. Paper made it, the astronauts unfortunately were too big. Mess.
There was the debate of, hey, you want to put all this cool stuff?
Oh yeah.
Personalized, this stuff is ours, and it goes off to space. Like, how cool to say, this went up to the edge of our atmosphere into space.
Also, not picture, there's also a muffin we want to put in there, which we can say we went to space and ate it, and hopefully not get cancer from all the radiation. Unfortunately, the cancer muffin did not make it to space.
This is what they did when we were not looking. And the discussion came up with, what happens if we don't get it back? Don't put anything valuable when you want back. Just in case. So this is a few more pictures of us designing the balloon here, just to give you an idea, because we're going to show you a bit of a challenge that happened here. Take note of this part here. This is part of the balloon. We have successfully duct taped this thing up. So the big hose comes out here, and once you're done filling it, you have to fold it up, duct tape it, and there's wire, there's string, there's zip tie, trying to make sure this thing doesn't fly away. We had a lot, so just take a look at the complexity there. There's a reason why. And just to kind of note here, this stuff does not happen on its own. We had a lot of help from coworkers. You might not see in the background of the pictures, or kind of some people from last year. These are my true science students here. More science people. These were the individuals. Missionaries who made the video that you're watching. There's a lot of the video process.
Work on the Arduino and all the computer stuff that we have no idea how it works.
And everything going for
Dad's scared. He released the balloon the first time.
So if it wasn't for these coworkers and the dedication of them, nothing like this actually goes on. So it doesn't happen in isolation. We have to show you, because our video doesn't really show it, the nice video that we have. So we thought we'd explain to you the challenges, because one of the ideas of working with science like this, hands-on projects, that it doesn't always go the way you want it to. We learned this from the first part, the helium balloon linking, losing the balloon, things don't always go the way you want them to.
Each year there are different challenges. Not everything goes right in one. Like something may go right the first year, a different thing might go wrong. Pay close attention to our reactions. Took us a moment to kind of register the situation.
So at this point, besides the blood sugar hitting the center of the earth, we had to take down the balloon, dismantle that picture I showed you, duct tape and everything else, without destroying and tearing the balloon. Because if we tear this balloon, if one thing happens to it, it's game over.
Well, except we had a spare balloon. Except, remember what happened last year, or 2015, and how Shaftesbury was oh so kind to give us their spare balloon? Well, last year, their balloon ended up going bye-bye. So we had a spare balloon, which we gave back to them, so the debt has been paid off between us.
And you saw that camaraderie coming in here. So we were, with Shaftesbury lost their balloon this launch, we ran over, helped them, and as soon as this happened to us, they ran over and helped us prepare the, it shows it towards the end here. And then the chase was on. Yeah, so this was a particular chase here. We had to go back down kind of the side roads of the southern parts of Manitoba here to find the balloon. Now this was the tricky part, because we had our radio licenses. We even bought a spot tracker, we rented from Wilderness Supply, a spot tracker in there, and I gave the website address to one friend and said that if anything shall happen to this balloon, tell me where it is, just in case.
Always have a backup plan.
And sure enough, halfway through, so about an hour, we get it up there, it launches, we're like, we got this. I'm on the Yesu, I'm next door to the subway, and the signal stops. We're not getting anything from the balloon. All those months of studying for the flight. And eventually, after about an hour, we got one signal aimed back to us on our little Yesu.
Joy.
So we were able able to track it down. We're on the side of the road there. What I had to do was take the coordinates from the ASU, because it actually spits out a longitude, latitude, and I pulled out my GPS, a little Garmin, typed in the exact coordinates. Your destination is 500 meters to the right.
Recalculating.
And this is all of us. So the kids ran. We parked off to the side of the road first.
Running dusty conditions does not feel good.
It looks really soft there. It's not. It's so soft.
Lots of mud and dust. It's just wonderful.
This was the first time that Jasper High School and all high schools actually saw the balloons come down. So this was a kind of a milestone in the global space balloon launch year. So this was pretty amazing that we saw all the balloons on big cut. So this is our opening of the payload here.
Our parachute route this year. So both our boxes were in one piece.
Oh no, we didn't tell them why the box stopped.
Well, once again, the muffin didn't go in the box because it was too heavy.
As soon as you turn your head, the students are like, we're going to radiate this muffin. So the joke was that I went to Tim Hortons, bought all these muffins and coffee donuts to the kids. They stuffed one of the muffins inside the payload. And Jasper ran over and said, you need to take a mass of the payloads. We tear over the payload. Here's just this muffin.
Well, told us we could put it in the payload. The chapter was cheering us on.
The chapter did not tell us, so we tear open, and there was a big joke about how muffins are so nice that they ruin science.
Hortons can sponsor us next year.
You never know. This was our launch from this year here, just to show you. So our GPS completely crapped out at some point that we don't know why. We asked amateur radios who were there to help us out as well. They had no explanation.
Technology. And here's our remains from last year. So once again, part of the balloon. The oh-so-tangled stabilizers, and our parachute that actually worked.
So this was the launch here at Carmen. The GPS craps out, and then there's this signal here, and my heart jumps with joy, and this is the last signal down here where we were actually able to retrieve those. So this is just another view of the weirdness that happens within launch. Only Maple Street is this. We thought it was hilarious that this little tiny bump right here, and see it comes upside down.
You know what happened there. Also, more technical errors with that, considering footage.
I want to show you a few slides of the images we did get back, because we had better technology. We had neutrinos, we had our GPS unit back in there, and we also had
HD cameras also. We had better quality cameras, so we get less fuzzy pictures.
Just to show you an idea at the time. So we had one camera pointing straight down, one pointing straight up. And this will show you the growth of the balloon as it hits the upper atmosphere. So this is just at launch over time, and this is just about the balloon burst here. And we realized we needed external batteries.
Well, it would have if it wasn't for that little mishap. Because what happened was when the balloon came down, a lot of time elapsed between the failure of the first launch and the success of the second launch. So the batteries in the good camera unfortunately ran out. So we couldn't get all of the footage we wanted to. Sad face.
But we were successful in getting a lot of great videos, and we had enough money left over that we, for next year, we got a GoPro. Great. I will. There were 2 more slides to work on here. This is our year from this year.
Manitoba, you have VA or VE.
See any signs of a smoke valve there, traffic control before you launch?
I love that in the hands of the very experienced Mr. Bob Streamer. The deal is, if we had a 12-kilogram balloon, that was one of one of our first questions. They said you don't have to take home. It is 1,200 kilograms. You cannot launch near any airports. If you have a 1,600-kilogram balloon, you can determine.
Any other questions?
How did all the other balloons fare when they were all launched together then? Did they all come down the same place? Did they go to the same height? What was the story there?
All the balloons, just about. They all pretty much went to the same height and pretty much came down within the same area. It might have been off by a little bit, a few meters, but we were very close to each other.
Adam?
Yeah, this is a really a mind-blowing project. That is so cool that we were able to pull that off. And to see the curvature of the Earth, too, was really, I don't know, it's just mind-blowing. It's unreal. Now that you have your radio license, are you going to be starting a ham club?
30 is a ham club.
Is it really?
Yeah, they meet at Shaftesbury. I forget.
Well, congratulations. I mean, that's really something. It's amazing.
Very good.
We were skittish because we lost the first balloon the second time around. Like the first time we lost it, so the second time around we're supposed to do a lift test. And we had the proper thing to, if the deal is, if it lifts 1 kilogram out of water off, you're good. But we were hanging on to it, and we duct taped the balloon to our PVC pipe just to start. But we were kind of hanging on to it when we did it, so our calculations just because of that handhold we were doing, we didn't put enough fueling into it, so we ended up having to take it apart and pump water.
And those are astronauts.
Are the YouTube videos available from this site as well?
Yes, our video is up on YouTube, but you might have to go to this website here to get it. But if you Google it on YouTube, it might come up.
And also, did you mention that you can't use any larger balloon without a license?
We can use 1,200-gram balloons with a radio license. If you use a 1,600-gram balloon, you need a permit to launch it. This was the highest, the biggest balloon we could get in our range of safety.
For extra challenge, you could try a night launch with LEDs on, you know? Then you're really putting faith in the AC.
We would love to do it. We talked about doing a night launch with cross our fingers on the door. That would be the top. Any other questions?
Put in a certain amount of helium to hold the balloon at a certain level, let's say 110,000 feet for like 6 hours.
Sorry?
Let's say, if you put enough helium so we just hover at, let's say, 110,000 feet for 6 hours, and then come down here, it would go too far.
Probably could. We don't want it to do that.
We only have so much time as students because, well, we have to get permission in order to go, and if we're out all day, that might be problematic for other students' schedules.
They do that in Antarctica, but you have to have venting system because it warms up during the day and cools at night and will sink. So you actually have to carry a little extra with you or dump ballast to keep it at a constant altitude. It's also a pressurized balloon, and then this kind of balloon. Okay, we're done. Thank you very much.